The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Thank you, Sharia, for a nice introduction. And the snow doesn't leave me alone. I'm from South Dakota, and we had 2 feet of snow last night. And they're just chasing me here. Good afternoon. As Sharia said, I'm Mostafa Tazarv, assistant professor at South Dakota State University, and I would like to thank my colleagues in this project. Lucas Bohn was the master's student, graduated last year, and Dr. Nadim Wehbe, who was the co-PI of the project. And I would like also to thank the sponsors of the project, South Dakota Department of Transportation, U.S. Department of Transportation through UTC, Mountain Plain Consortium, and many companies that who worked with us through this project by donating materials and time, HRC, Lafarge, Forterra, and I really appreciate and thank them for direct support. Another good news that I have for you, I'm the first person in the seismic presentation who is not going to show you anything regarding seismic. But this is one of the issues that you would see in many of the bridges. I'm going to talk about double T bridges and how we are going to retrofit the longitudinal joints of 2 precast girders. And just actually to give you an introduction, double T bridge, we can see the section down there here is around 4 feet wide and 2 feet deep. And the way that they're constructed are they just put them side by side. There are steel angles every 5 feet along the length of the girders, and on field they just weld another small plate to the existing angles, and they fill the key with the grout. That's essentially how precast pre-tension double T bridge is constructed. That's fairly common in South Dakota on the local roads. We have more than 700 of those. And I know that many of the neighboring states have this kind of the bridge. And in parking buildings, you can see also this kind of actually girders. And I know that Texas and Alaska also use this. So the issue that I'm going to raise today, and hopefully to give you some answers, is not just for South Dakota, you would see in many other states. The issue is both structural performance and durability and serviceability. After 5 to 10 years of service on the field, what happens is the joint deteriorates, and because of the salt that used because of the snow, and the deterioration of this joint is faster than what you would see, let's say, in California. And basically, after 40 years of the service, DOT ends up replacing these girders while they should last at least 75 years. So that's not the case. That's actually the durability issue. And Dr. Wehbe, who was the co-PI of this project, also did a full-scale test of this bridge, 40 feet long, 2 of the girders side by side. He used the conventional detailing that I showed you, and he tested the girders to failure. You can see that the bridge unzipped, and essentially you have 2 girders that don't talk to each other, don't transfer loads. So they can meet AASHTO service limited state, but they cannot meet AASHTO strength limited state. So absolutely this design, this joint, after 20, 30 years would make your design unsafe. So essentially one of the girders is taking the full load of the truck rather than being distributing. Here we can see force deformation behavior of the full-scale bridge that Dr. Wehbe tested. You can see right after the service, this joint start to cracks, and the force deformation of two girders doesn't follow each other. One is unloaded, another one is taking the load and going to failure. So my job here is to show you the technique that we came up with to repair it, what I could retrofit it, and hopefully to extend the life of the bridge for another 75 years rather than replacing them. To be able to do that, I need to introduce latex modified concrete. I don't have any specific slide for that, but I do have one for ultra high performance, which is kind of hot topic right now. But here is what essentially UHPC is. It's a cementitious material with very fine aggregate. They make old sands and a gravel with the size of dust and mix them up, make a honey-like material, they pour, and that's UHPC. 2% steel fibers is usually used, and in the lab, the strength can get to 36,000 psi. When you hit it with hammer, you can hear sounds of steel while it's concrete. And on field, you can easily get to 18,000 psi. Down there, here is a stress strain diagram of concrete in compression, and that's UHPC. 5 times stronger, 5 times more ductile without any reinforcement, and tensile property is much better than conventional concrete. So this is one of the material that we use in this study. What we essentially did it was we did an extensive literature review. We came up with 20 joint rehabilitation detailing. Then we came up with a rating system. The rating system told us that 4 of those options would be the best for rehabilitation of this kind of bridge. And then we did 13 larger scale beam tests to optimize our detailing. We also did finite element analysis to come up with the smallest possible sizes of the repair. Then we tested one full scale bridge for around 50 years of service life. We basically massaged the bridge, saw some preliminary damage. Then we did the rehabilitation. We tested the bridge for fatigue and ultimate testing. Because of the interest of the time, I would only show you the result of rehabilitation, how we did the rehabilitation, how was the result, and at the end, like recommendations that we made. We tested a full-scale 40 feet long bridge, and the way that we built it up, we asked a contractor for Terra down in Mitchell, South Dakota, to build these 2 girders. We put them side by side. We followed exact detailing that has been used on field. We asked a licensed welder to come and do all of those steel weld for us. We try to be as real as we can that will be used on field. And we started testing this bridge. We massaged this bridge for, I don't know, maybe 40, 70 years of service life, and then we perform rehabilitation. We didn't want to rehabilitate in new bridge, so let's put it that way. And then we had all kind of sensors in it. When you stay here, that's what you would see on the bridge, and you can assume that would be me. So that's the geometry of the bridge. We did 5 tests. We started with testing of conventional bridge, then we tested the conventional bridge up to the service limit just to crack the longitudinal joint, and then we rehabilitated, tested under fatigue 2, AASHTO fatigue 2 loading for 500,000 cycle, AASHTO fatigue 1, which is not really the case here. This bridge is going to be used on local roads, so fatigue 1 really doesn't stand there. That's for high traffic volume area. But we did it just to make sure that the bridge is strong enough with the rehabilitation, and we did ultimate testing. As I said, the bridge was heavily instrumented with different kind of instruments, strain gauges, LVDTs, and actually load cells. And to give you a general idea of what we did, out of those 5 element and 13 beam column tests we did, we came up with 2 rehabilitation method. Rather than testing 2 full-scale bridge, we came up with testing 1 full-scale bridge, but using those 2 methods on half of the bridge. On this half of the bridge, I'm going to call it a continuous joint. We poured latex modified concrete, and all our previous studies were essentially saying that the durability of this material is good. So that's why we used it, and we didn't use conventional grout here. That was the reason. And on this portion of the bridge, we came up with this pocket idea to reduce material and actually cost. And we use it ultra high performance concrete or UHPC in this one. So this one, I'm going to call it pocket ID or pocket connection, and that one is the continuous one. The way that we did the rehabilitation after the testing of the full-scale bridge is we asked a licensed contractor to come to our lab and perform those shapes that and make those shapes that I just showed. So essentially what they did, they cut 1 inch deep and then they demo concrete. The goal was to use exposed bars of the deck and in actually either of the two cases and put some reinforcement to make sure that we are going to tie the two girders together. All of those previous studies were to optimize the size of the joint, the spacing, which was 5 feet and the size 18 by 18, or I guess 15 inches here and continuous one. So this side, we filled it with latex modified concrete, and this half of the bridge, we filled it with ultra performance concrete. And here we can see how we poured latex and a UHPC on field. That was essentially very easy. The only issue with UHPC is, at least for us, we didn't have large volume actually shear mixer. That was an issue for us, but on field they can go with huge capacity, large capacity shear actually mixer. That would be only issue because it needs 20 minutes of mix, and more powerful machine would give you that option. Before we do any testing, we have seen shrinkage crack on the latex modified side. And just like to zoom in, that was one of the girders, that's another girder. That's the continuous joint that we filled with latex modified concrete. And that one is just before doing any testing. We saw this parallel like shrinkage cracking. And just by seeing this, our recommendation is don't use latex modified concrete or any kind of conventional grout here, because of the boundary condition, you would see a shrinkage crack. They call that restrained shrinkage crack. So that was a hard way to learn, don't use that material. But anyway, we decided to continue the testing. This is the picture of the bridge underneath. We had water dam on top of the bridge on every of these joints, so you can see the water leak, so it was pretty bad. And if you want to use it on cold region, this guy would deteriorate very fast. So it's not an option really for the cold area. So our recommendation is don't use it. This is the way that we did our fatigue testing. This one is AASHTO 2. We apply 21,000 pounds every second. And here is the result of both phase of the fatigue testing. This is AASHTO fatigue 2, which is for local load essentially. For 500,000 based on ADT average daily truck traffic of 15, which is actually a good number for South Dakota local roads. It is equivalent to 97 years of service life. For 97 years of service life, the stiffness of the bridge didn't deteriorate at all, and it gained some stiffness. It can be only measurement issue, but you can see that there was no change in the stiffness. So we can say that at least from the service life, it's good. We did also AASHTO fatigue 1 testing, which is essentially double of the force that we applied in fatigue 2. This is for high traffic area, and again, we didn't see any significant change in the stiffness. So our conclusion was, even though there was shrinkage crack on half of the side of the bridge, overall there is no change in the stiffness. Those shrinkage crack doesn't affect the structural performance. So overall, both when you combine them, we tested the bridge for more than 100 years of like service life, and no change in the stiffness of the bridge. And then we performed the ultimate testing. Our speed was very low, and I have these arrows for you to see how ductile the bridge was. The speed of testing was 0.007 inches per second, so we did this testing in about 4 hours. You are seeing that in 30 seconds. The speed of the video is actually 64. So you can see that the bridge is bending here, and it's essentially failed in very ductile manner. I would give you a specification for that. Another thing I wanted to mention here is for both fatigue and ultimate testing, rather than putting the load exactly at the center line of the bridge, we offsetted the load and put it on one of the girders. The goal was to see if the joint would survive this extreme condition and would it be strong enough to take the load from one girder and pass it to another one. So the load was offset, and here is the damage of the bridge during the ultimate testing. At the beginning, we had very typical damages. The crack started at the middle of the girder, very close under the applied load, and then the crack propagated, got bigger, and at the end, the girder failed, or the bridge failed by compression failure of the deck itself. And you can see the condition of the bridge after the failure. Here is the damage of the two joints, the two rehabilitation methods that we had. That one is the UHPC. At the failure of the girder, we had minor cracks at the edge of the pocket. And here is the damage of the continuous joint. At the failure of the girder, we had insignificant damage of the girder. By taking a look at this, you can tell the joint, the actually rehabilitation method was strong enough to take the loads to sustain all of the formation and cause girder failure. So it was sufficient to do that. And here is force deformation of each girder. You can see up to the failure, both girders perform monolithically. Put it in a very simple way, it's like that you cast both at the same time. So both girders perform the same up to failure, and there was no change in force deformation behavior of the two girders that we had, and we connected through these two methods. We also had the strain gauges inside the joints. At the failure of the girders, at the failure of the bridge, the strain inside, the strain of reinforcement inside the pocket was less than yielding, means that we met the capacity protected requirements of the AASHTO at the failure of the girder. That was fine too as well. And here is the evaluation of the bridge with the previous conventional double T bridge. The green line here is the stiffness versus the number of applied load. The green one is what is being used right now, the conventional double T. You can see after a few thousands of fatigue testing, the stiffness deteriorated very fast. And then the red one is the new joint detailing that Dr. Wehbe came up to fix this issue for the new construction, and the black one is the one that we came up with to repair the current double Ts. You can see absolutely no change in the stiffness of the bridge, while the conventional one deteriorates very fast. This is AASHTO fatigue 2, this is AASHTO fatigue 1, we saw the same thing over. So actually, as a general rule, this rehabilitation detailing is so powerful that it's like that you cast the bridge all at site. So it would act as actually monolithic CIP bridge. And here's force deformation, same color. This is conventional double T. It didn't meet AASHTO strength limits requirement because it's failed here, while the new joint detailing and rehabilitated one failed in the same manner, ductile manner, and met all of the requirements of the AASHTO. Means that again that both both rehabilitation, detailing very structurally viable. And we did also cost estimate. We asked a contractor to do this cost estimate. With the pocket idea, the cost of rehabilitation is only 30% of the bridge replacement. And with the pocket one, your cost would be half of that. So regardless of which method you are going to pick, you are going to save lots of money. And we asked the contractor, pocket, continuous, which one you would like to pick on field. They said that pocket, because it was much easier for them to form those joints rather than make it continuous. And in terms of structural performance, was better, or it was acceptable, both cases. And in terms of cost, pocket would save you 70% with respect to replacement. So as a conclusion, I would say that both pocket and continuous detailings are viable, but you cannot use non-shrink grout, concrete, SCC in the joint. You have to use a better material like UHPC. The pocket idea with UHPC works just fine. You can save money by using smaller joints and getting very good structural performance. So our recommendation is go with pocket idea, because it's structurally viable and reasonable. And if you're interested to learn more about this project, you can go to my website, download the report, and I also have the final recommendation for you if you want to take a look at that. The idea is just form these pockets along the longitudinal joints of the member. You put some reinforcement here are detailing, nothing specific, number 5, 4 of those in any direction, 1 continuous, 2 continuous, 1, and fill it with UHPC. That would be your recommendation. Sharia, that was all. I have some more, but just in case if there is any question.